Question 3. Part A. Find the remainder when 2x cubed minus 5x squared minus 4x plus 1 is divided by x plus 3. Well, you can just substitute in x equals negative 3 into this equation. So then this gives you 2 times negative 3 cubed minus 5 times negative 3 squared minus 4, oh my goodness, minus 4 times negative 3 plus 1, and that gives you negative 86. Okay, that's it. Part B, simplify this negative 1 plus I to the power of 6 over root 3 plus I to the power of 4 and leave it in polar form. So if you want to leave it in polar form, you should probably do it in polar form first. So convert negative 1 plus I into polar form. So for the first one, the modulus is equal to the square root of 1 squared plus 1 squared, which is just root 2. And then the argument is going to be the inverse tangent of 1 over negative 1, which gives you negative pi over 4. You can kind of justify that as well by looking at it on an Argand diagram. It's going to be at, it's at negative 1. So it should be at negative 1 and then I over here. So it's actually situated over here. So it's actually pi over 4 here, but then an extra pi over 2 over here. So all in all, it should be 3 pi over 4, not negative pi over 4. Okay, you should probably draw them all out, always, just to make sure, because I got that wrong. Anyways, so and then the bottom one, the modulus is going to be the square root of root 3 squared plus 1 squared, which then gives you root 4, which is 2. And then the argument is going to be the inverse tangent of 1 over root 3. Yep. Which gives you inverse tangent of 1 over root 3 pi over 6. Okay, so now converting this into polar form, you have root 2 cis of 3 pi over 4, and all of this is to the power of 6 divided by 2 cis of pi over 6 to the power of 4. So then using your de Moivre's theorem, root 2 to the power of 6, that is going to be a great question. Root 2 to the power of 6 gives you 8. 8, and then multiplying the argument inside by the power is going to be 6 times 3 pi over 4. It's going to be 18 pi over 4, which you can then take out 2, so it'll be cis of 9 pi over 2 over 2 to the power of 4 is 16. Cis of 4 times pi over 6 is going to be 4 pi over 6, or 2 pi over 3. And then because it's two polar forms divided by each other, this is going to be 1/2 cis of 9 pi over 2 minus 2 pi over 3. So it's going to be 1/2 of cis. Well, in order to take the difference between them, you need to make the denominators equal to each other. So you multiply this by 3 over 3 and this one by 2 over 2. So you're left with 27 pi minus 4 pi over 6, which gives you half of cis times 23 pi over 6. Okay. On to part C. Part C is one solution of the equation 3z cubed plus pz squared plus qz minus 20 equals 0 is that z equals 2 plus I, conjugate root theorem, z equals 2 minus I. If p and q are real, find the other values of p and q and the other two roots of the equation. So we just need to find the third root and the values of p and q. But essentially, we just need to substitute in this z into this equation. So let's first figure out what z squared is. 2 plus I squared, which gives us 4 plus 4I plus I squared, which then gives us 3 plus 4I. Z cubed is going to be 3 plus 4I multiplied by another 2 plus I, which then gives us 6 plus 3I plus 8I plus 4I squared, which gives us 2 plus 11I. So then let's substitute this inside this equation. 3 times 2 plus 11I, right? Plus p times 3 plus 4I plus q times 2 plus I minus 20 equals 0. So then let's expand everything out. This gives us 6 plus 33I plus 3p plus 4pi plus 2q plus qi minus 20 equals 0. Grouping all the real parts is going to be negative 14 plus 3p plus 2q. And the imaginary parts is going to be 33 plus 4p plus q equals 0. And each of the real parts and the imaginary parts need to equal 0. So we're going to set them equal to 0. So negative 14 plus 3p plus 2q equals 0. And then 33 plus 4p plus q equals 0. So in other words, 3p, that should be 3p plus 2q equals 14, and 4p plus q equals 33. So then again, just using your calculator to solve the simultaneous equation. And you have 3, 2, 14, 4, 1, 33. So then p is equal to 10.4, q is equal to negative 8.6. So then your equation is z cubed plus 10.4 z squared minus 8.6 z minus 20 equals 0. Solving this in your calculator again, fill in your coefficients. 1, 10.4 minus 8.6 minus 20, and that should give you, oh sorry, there should be a 3 in front. Hmm. 10.4. It's not what the answer should be. This should be equal to negative 33. So then your p and q values are going to be different. That should be negative 33. And so p equals to negative 16. Q is equal to 31. So then your equation should be 3z cubed minus 16z squared plus 31z minus 20 equals 0. Then you can solve this in your polynomial function with 3, negative 16, 31, and minus 20. And then your final solution should be z is equal to 4 over 3. So those are your 3 solutions. 1, 2, 3. Okay. Next question is going to be part D. solve the inequality of z minus 3 being less than z. So again, we know that z is just a complex number, x plus iy. So then this is just x plus iy minus 3 less than x plus iy. So then taking the modulus of this, so the real part is just x minus 3 squared, and the imaginary part being y squared, less than square root of x squared plus y squared. You can square both sides and then expand out the left side brackets as well to get x squared minus 6x plus 9 plus y squared less than x squared plus y squared. Notice that the x squareds and y squareds, they cancel each other out. So you're left with negative 6x plus 9 greater than 0. Or in other words, 9 greater than 6x, or x is less than 9 over 6, or 3 over 2. So then on a graph, it would look like this. 3 over 2. And this line is x equals 3 over 2. And everything less than that. So it's all of this side here. Okay. Moving on to the final part, part E. Find the range of values for k, positive real number, for which the solutions of z are purely imaginary for the equation. Okay, let's see, the equation is z plus 4i over k times 1 over z minus 4i over k equals 1. Okay. And we're just solving for z. And we don't necessarily need it to convert it to a complex number x plus iy. So let's just work with z like this, and let's expand out the brackets here. So expanding this out, you get z over z, which is just 1, and then minus 4i over k times z, and then plus 4i over kz, and then minus 16i squared over k squared is equal to 1. The 1's cancel each other out, and then what I'm left over with is negative 4iz over k plus 4i over kz, and then the negative 16i squared becomes positive 16i squared because the I squared is negative 1, so plus 16 over k squared, and this equals to 0. There's a factor of 4 everywhere, so we can get rid of the 4. This becomes a 4 over here. So I'm left with negative iz over k plus I over kz plus 4 over k squared equals 0. I need to join all these fractions together. So I need to multiply everything to get a common denominator of k squared z. So I need to multiply the left side by kz over kz, the middle one by just k over k, and the last one by z over z. So I'm left with negative k I z squared plus ik plus 4z over k squared z equals 0. I can multiply the k squared z to the other side and it becomes nothing. So all I'm left with is negative ki z squared plus 4z plus ik equals 0. And then I can solve for z by using the quadratic formula. Z is equal to negative b, which is negative 4, plus minus the square root of b squared, which is 16, minus 4 times a, which is negative ki, times by c, which is ik, over 2 times a, which is negative ki. So then this gives me negative 4 plus minus the square root of 16, and I've got here negative ki times ik. Well, they're the same thing. This negative in front multiplies with the negative there to give me positive. But then I've got I squared over here, which gives me a negative. So it's a negative times a negative times a negative. There's 3 negatives overall give a negative. So it's minus 4k squared over negative 2ki. Okay, we can factorize this inside over here with a factor of 4. So you get negative 4 plus minus the square root of 4 times 4 minus k squared over here over negative 2ki. And then this square root 4 can go out as a 2. So then this is negative 4 plus minus 2 square root 4 minus k squared over negative 2ki. So then this is, you can take out the 2 here. So you're just left with minus 2 over here. And there's a minus here as well, so you can reverse the order of the... Actually, we don't have to do that yet, because we're going to have to rationalize the denominator anyways. So you're going to multiply this by I over I. So all you're left with is negative 2 plus minus the square root of 4 minus k squared, all multiplied by I, over negative ki squared. And the I squared becomes negative, so it's just negative times negative becomes positive. So this is probably the simplest expression you can get for the solutions for z. And you can see that, well, we want this to be purely imaginary. So z is equal to this, we want this to be purely imaginary. You would think that because the I is multiplied by all of this, that all of this is purely imaginary. But if this square root inside here, if what you're square rooting is negative, or in other words, if 4 minus k squared is less than 0, then this implies that square root of 4 minus k squared is going to be imaginary. If that's imaginary, and you're multiplying the imaginary number by another imaginary number, then you're going to get a real number, right? Because you're going to get I times I. So then, this means that 4 minus k squared must be greater than 0. Therefore, 4 minus k squared must be greater than 0 if z is purely imaginary. So then you can solve for k, 4 being greater than k squared, or plus minus 2 being greater than k. So what does this actually look like in terms of the solutions here? So this is a negative, right? So it's a negative quadratic. So it looks like this, where the intersections are negative 2 and positive 2. And we're interested in when this is positive, so that the square root is going to be positive. So it's going to be this area over here that is above the x-axis. So we're only interested in the k values between 2 and negative 2. So those are the k values that make z purely imaginary. And that's all they wanted. And that's the end of the paper. Hope this helps. Yeah, I'm going to end it there. Thank you.